So in this video, we're going to talk about the speed limitations of OpAmps. So one of the other assumptions that we made when we introduced an ideal OpAmp was that it reacts instantly to the changes at the input. Well, physically, we know that's not going to happen, right? So we're going to have a little bit of time that, the circuit has some delay to it and all that, right? So what is going to happen is that when you look at the OpAmp characteristics, in terms of the frequency response especially, if I want to plot that, the way the OpAmps are designed, so this is your OpAmp. If you look at V out over the differential input, right? Basically the characteristic curve, the frequency response of the system, right? And these are log scales. So in here I have omega, the frequency of the input signal, and over there I'm looking at the magnitude of the gain of this amplifier. If I look at it over the frequency range, this is typically what you see. So you see a finite input gain, some finite gain, right? This is our AV naught. Ideally, we know this had to be infinite, but practically it's not infinite. So it's 1,000,000, 100,000, some large number. And this infinite gain goes all the way to some frequency, let's just call it omega b. So you have a relatively constant gain all the way to that frequency, and then it starts to drop at a constant rate. If you look at how it drops, how fast it drops, it's about minus 20 dB per decade, meaning that for each decade of increase in frequency, the signal amplitude drops by a factor of 10, right? So let's say if the gain is somewhere in that mid-range, let's say at 100 hertz, let's say the gain is 100,000. At 1 kilohertz, 1 decade higher in frequency, the gain goes from 100,000 to 10,000, right? So this behavior is similar to what you had for an RC circuit. A low-pass RC circuit would behave the same. Well, obviously, the gain magnitude is, this is a high-pass. The gain magnitude is less than 1 in all situations. But a low-pass system is a single pole system, right? You just have 1 plus RCS in the denominator of your transfer function, and you would see a similar pattern over there, that 20 dB per decade of signal intensity, let's say loss over time, over frequency, and some fixed range of frequencies at the beginning where the output is basically following the input. So this is by design. This is intentional. So the way that the circuit designers, IC designers design the OpAmps, they spend quite a bit of time actually to get this kind of a behavior from the circuit. You can guess that you have a circuit made of, let's say, 20, 30 transistors with all sorts of resistors and capacitors. Each transistor has at least 3 parasitic capacitors. So you can imagine how many poles and zeros you will have in that circuit. But by design and through some frequency compensation techniques, they make the circuit to behave like this when you look at it from outside. So it behaves like a single pole system. So you have a frequency where the gain starts to drop, and you have a frequency down here where the gain actually becomes 1. So if you look at 20 log, it's 0 dB gain if you want in log, or a gain of 1. Basically, the OpAmp does not have a gain anymore. So let's say your voltage gain drops to 1, right? You do not have any gain anymore, or 0 dB. Now, if you have a transfer function like this, you can show it with an expression as here. So your frequency-dependent gain is now your AV naught divided by 1 plus S over omega b. Right? So omega B is this corner frequency. So after that, the gain starts to drop. At that frequency, actually, the gain has already dropped by 3 dB. So maybe I should actually put it here. So this is your minus 3 dB point, right? And we know why minus 3 dB is important from the circuit theory or control theory. Minus 3 dB for the signal amplitude means that your signal power has halved. You have half the signal power at this point, 0.7 in terms of amplitude. Okay, so this is how I can model that, right? So it's knowing that I can look at the op-amps in most situations, and they're designed to behave like a single pole system. The transfer function can be written as this, right? So I know AV naught is large. Omega B for most op-amps, if you go and talk about, so omega B is 2FB, right? Or omega T here is 2 pi FT. Omega B is 2 pi FB. So sometimes it's easier to talk about these frequencies in hertz. So FB for most op-amps is a small number. It's on the order of 10 to maybe 100 hertz, maybe in some cases kilohertz. And FT is the maximum frequency that you would like to use this op-amp. Beyond that, your gain is less than 1. There's no point in using the op-amp. That can range anywhere from maybe a few tens of kilohertz to all the way somewhere around 100 megahertz or even gigahertz. So this is your typical op-amp. Let's see how this behavior for the gain values. So far we assumed it was a constant at all frequencies, but now we know it is not. Let's see how it affects the behavior of my circuit. So let's go back to the non-inverting amplifier. Or inverting, it doesn't really matter. The analysis applies very, very similarly to both cases. Where I had this circuit, right? So I'm going to assume that the op-amp is ideal otherwise. The only limitation is the speed limitation. So I use the golden rules and all that to get the gain. But because of the limited gain, right, I have some limitation. I know the input-output relationship for this circuit. If the gain was constant, we did the calculation for the inverting situation, it's going to be the same for the non-inverting amplifier. So if it was ideal, it would be this. If I had infinite gain, I would have that equation, that expression. For an op-amp that has a finite gain, I will have this expression. Right? So we saw that before. For an inverting amplifier, the numerator here would be minus R2 over R1, right? But the denominator is the same. Now, just so that we save on writing, let's just call this G, right? So the ideal gain, let me just call it ideal gain, which is the ratio of the two resistors given by the ratio of the two resistors. Let me call it G. Right? So I can write V out over V in as this. So it's G over 1 plus G over AV naught. Now, this is for the case that my gain is not infinite. If the gain is infinite, again, you can see that the G over AV naught ratio will go to 0, and then I'm back to my ideal gain. Now, let's assume that I actually, in addition to having a finite gain, I have this frequency-dependent response as well. So what I do is that instead of using AV naught in that expression that I have at the bottom, I use this expression that is frequency-dependent. So instead of AV naught, I'm going to use AVS. Okay? So this is going to be, the rest of the calculation doesn't change, right? The resistors, all those things are frequency-independent. So I will have G over AVS. AVS is some AV naught divided by 1 plus S over omega B. Okay? Maybe for 1 second, let me go back here and just explain how this graph is produced before we go any further. So what I'm plotting here is the amplitude of the transfer function. So the amplitude of AVS or AVJ omega, right? If you look at it, it's going to be AV naught over the square root of 1 plus omega over omega b d squared, right? So 1 squared plus omega over omega b squared. So I replace s with j omega, so I have a complex number. The real part, imaginary part squared, take the square root. So if you look at this closely, you know, at very small omega, if omega is much smaller than omega b, so if omega goes to 0, this second term is negligible and AV approaches AV naught. If omega goes to infinity, if omega is, or let's say the other way of saying it is, if omega is much, much bigger than omega b, then what happens is that you can ignore the 1 here in this expression, and you get AV that is AV naught divided by, let's say, omega over omega b, right? So basically, it's going to stop, or AV naught omega b divided by omega. The only variable here is omega, so the gain will drop linearly with increase in frequency, and that's how you can plot that curve. And we'll see why we needed to make this jump here back to that expression if you just didn't know how to do that. But going back to the bottom here, so this is our expression, and I can expand this and see what happens. So this is going to be, again, G over what do I have here? So G over A V naught times 1 plus S over omega B plus 1, okay? And if I expand that a bit, it's going to be G, my DC gain, over 1 plus G over AV naught plus S over, and I'm going to write it like this, AV naught omega B, okay, divided by G. Okay? And for now, let's assume that the gain, the DC gain that we're getting out of this circuit is much less than AV naught. So basically 1 plus R2 over R1 is much less than AV naught, meaning that, you know, I'm getting a gain of, let's say, 1,000 out of an op-amp that has an open loop gain of 1,000,000, right? So if that's the case, what you can do is that you can ignore this term here and come to a more simple expression. So it's going to be G over 1 plus S over AV naught divided by G times omega B. Okay? So what does this mean? Well, what it means is that, well, your new pole, the system has a new pole. This new pole is at this location. So originally, the pole was at omega B, right? This is where the pole was originally. By putting feedback around this circuit, with negative feedback, new pole is at AV naught over G times omega B. Okay, so that's interesting. What it tells me is that, well, let me just rewrite this expression. The only variable here, you know, once you bind the op-amp is G. That's your 1 plus R2 over R1 ratio, right? That's the gain that you get out of the amplifier. So that's the only variable. The only thing that is changing when you change the gain of this amplifier is G, and you will have a new pole. Each time you get a new gain, you will get a new pole. We'll look at that location of that pole, but this number is constant. The numerator here is constant. So we give it a name. The gain bandwidth product is the name for that term, and that is AV naught times omega B. It is a constant. For a given op-amp, you design it to have a certain gain, you design it to have a certain initial point, bandwidth, that's a constant. And it's called gain bandwidth product. Now, for this circuit, this was the location of the pole. Let's look at the gain. So original gain was AV naught, right? That was my low frequency gain. In a case like this, if I look at this transfer function here, oops. If I look at this transfer function here, my low frequency gain is now G, right? The original transfer function is up here. So the low frequency gain here is, if we work before that corner frequency, lower frequencies. The original corner frequency was omega B. The original gain was AV naught because S is much smaller than omega B, right? In here, the original gain was the low frequency gain, or the new gain, is G, right? So if we operate at low frequencies, this S is divided by, let's say, AV naught G omega B is going to be small. We have a gain of G. Now, if you look at the product of the gain and bandwidth that I have in two cases. In the first case, the bandwidth that I had was omega B times AV naught. In the second case, the bandwidth is AV naught omega B divided by G times G. Now, in both cases, the gain bandwidth product is actually constant, is this value that you have here. And that's a property of these op-amp circuits. For all of these op-amp circuits, that corner frequency moves with your gain. Increase your gain, the corner frequency goes lower. Decrease your gain, let's say 1 plus R2 over R1, that's the gain I'm talking about. Lower that gain, your bandwidth increases. The product of the gain that you get out of that op-amp and its bandwidth, the frequency band that you can apply or amplify a signal, is constant. If you want to amplify, and I'll show you an example, but keep that in mind. So this is the main concept. The gain bandwidth product for one of these op-amp circuits, inverting or non-inverting amplifiers, these are your fundamental blocks, is constant. And easily you can find it. Once you have AV naught and omega B, you can calculate the bandwidth for any gain that you get out of this circuit. This product is also called when your gain drops to 1. So when AVS or AVJ omega drops to 1, what is that? So it means that AV naught over 1 plus J omega, so let's just call it omega T. J omega T over omega, but I'm looking at the amplitude, so this is squared, square root of that is 1. But omega T is much, much higher than omega B. You're talking about high frequencies now. So you can see that omega T is actually, at the end of the story, if you do the math, you can ignore the 1 here, and omega T is just equal to AV naught omega B. Right? So if you go back to that graph that we had here, this 0 dB gain, you can actually find it. It's AV naught times omega B. So for an op-amp, if I tell you that the omega T or FT of this op-amp, or the unity gain bandwidth of this op-amp is this much, you can go and calculate the gain bandwidth product. That's basically your gain bandwidth product, right? Gain of 1, frequency of omega T. So if I give you that value, that frequency, you have all the information that you need. Or I can give you AV naught and omega B. So I can tell you that this op-amp has a gain of 100,000. Omega B is, let's say, 10 hertz times 2 pi if you want to use radians per second or just 10 hertz, 2 pi cancels from both sides anyway. And then from that point onwards, you can figure out what is the possible gain you can get out of it, or what is the possible bandwidth for a given gain. So let's look at an example from your slides. In this example, this is from slide 28, which says we have an op-amp with AV naught equal 10 to the 6 volt per volt, and omega b of 2 pi times, 10 radians per second. And we are making an inverting amplifier with this op-amp. So for an inverting amplifier, with a gain of minus 100 volt per volt, what is the bandwidth, right? So, well, right now it should be easy for you to follow the discussion here. So we know that the gain bandwidth product is constant. So at low frequencies, open loop, the gain is 10 to the 6, bandwidth is 10. And under this new configuration, the gain is 100, but we don't know the new bandwidth. And then we can easily calculate the bandwidth from here, right? So bandwidth, let's say, is going to be 10 to the 7 divided by 100, so it's 10 to the 5 radians per second, which is about 15 kilohertz or so, right? So this amplifier has a gain of a gain bandwidth product of, let's say, 10 to the 7. For that kind of a gain, you get a bandwidth of 10 to the 5 radians per second. If I want to plot these gain values versus what happens to the bandwidth, originally you have a situation like this. So this is AV naught, and your gain starts to drop, and you hit omega t when gain is 1, right? So this is, let's say, omega t when gain is 1, or the amplitude, right? So this is the amplitude of AV. Okay, so this is your behavior, and then this corner frequency is omega b. Now, if you go and get some gain of 100 out of this, you go down this curve, so to somewhere like here, but whatever that you lose in terms of gain, going down from AV naught to some G, you gain in bandwidth. So you go up from omega b by G times that. So it's going to be G times omega b. And for different gains, it's going to be the same. So let's say G1, G2. It goes up to this and then starts to drop. Up to this and starts to drop. And they follow the same curve once they hit the 3 dB corner, right? But there is give and take, as usual. If you want more gain, you have to sacrifice bandwidth. If you want to have bandwidth, you have to give up some of the gain. So if you pick up an op-amp that has a, let's say, 1 megahertz omega ft, and you want to amplify a 10 kilohertz signal with it, you should know right away that you cannot really get a gain of more than 100 out of this. Actually, 100 is probably not even true, because that's exactly the corner frequency. So, if you need a lot of gain, let's say a gain of 1,000, you definitely cannot use a single op-amp anymore. You have to use a combination of op-amps, or maybe multiple op-amps in series with each other, right? But this issue of gain bandwidth products, so just keep that in mind. Gain times bandwidth is constant, right? So gain of 1, omega t, a maximum gain AV naught, you get omega b, and then anything in between will be basically following the same principle. So that's the OpAmp while it's still behaving as a linear element, right? It's just a linear element, it's single pole. You know, that pole make it behave like a low-pass circuit, but things are still linear. There is a speed limitation, as we just saw. You know, if you go very high in frequency, the amplitude of the gain will drop. But it is, you know, still, we can deal with it using linear system analysis. There is another limitation in the speed of the OpAmps that comes from what happens inside the package that is sold to you as the OpAmp, and it's a nonlinear phenomenon, and it is called slew rate. And it is another factor that limits the speed of an OpAmp. Basically what this means is that, let's assume that you have applied a signal to an OpAmp. Let me just use a buffer for now, just to make the drawing a bit simpler, right? Your V out should follow V in, and you know, this is a gain of 1, what can go wrong? And you go and apply a sizable signal, maybe, let me see, right? A large signal, you're looking at V in, that is a fairly strong signal, and you want to just buffer that and then take it and maybe, I don't know, use it to drive a speaker, which needs a lot of current, and therefore you use a buffer. And you connect it, you're saying, you know, my signal is, let's say, a 1 kilohertz signal. The omega t of my OpAmp is, let's say, 1 megahertz times 2 pi. So I shouldn't have any speed limitations here. My OpAmp should be able to amplify signals all the way to maybe about around a megahertz if I'm applying a 1 kilohertz signal here. So let's go and use it. And then you go and hook it up to your speaker, and then all of a sudden your ears are very sensitive to distortion. You hear a lot of unpleasant sounds. You go and look at the signal on your oscilloscope, and you notice that, you know, while the input is going up like this, and this is a buffer, so the output should match that, the output is actually moving on a straight line, right? It is trying to catch up to the input, but it never actually catches up to the input. It's always a straight line. And then it goes like that, and then it goes up like that. So instead of having a nice sinusoidal at the output, you see this distortion. You see this triangular waveform. Or if you go and apply a pulse, to the input, let's say same circuit, you apply a pulse. What you expect, if it is a single pole system, if it is my RC circuit and all that, what you expect is an exponential increase in the output, like what an RC circuit would do. And slowly over time, you should reach the final value. What you see instead is a behavior like this, that you apply your pulse and the output starts to increase as a ramp. And at some point, it gets close to the output, and then it becomes equal to the output. But it's changing much slower than you thought. You know, the single pole system goes up much quicker than the system that you're dealing with. And then the funny thing is that, you know, this looks like a ramp. In most cases, it's just like a straight line, a true ramp from the input all the way to very close to the final value, and then maybe it follows the exponential curve. So what's going on here? This slope, basically this slope here, dV out over dt. Once you hit this limitation, once you hit that ramp-like behavior, it's more or less constant. So it's independent of the amplitude of the input. If you applied a signal that was this big, you would see the same slope. If you applied the signal that was this big, you would see the same slope. More or less independent of the input. It becomes a characteristic of a device. It has its own name. So it's called the slew rate. and it is the maximum dV out over dt for your op-amp. Your dV out over dt cannot be larger than this. You know, even if your input is changing faster, even if you have a pulse or whatever, your output is not going to change faster than that rate. Why does that happen? Well, the reason is that, you know, inside that op-amp, as we said before, you have an army of transistors that are working together to amplify your small signal. And if your input signal is too large for these guys to handle, you actually push those devices, or some of them, out of their linear range. So all of a sudden, you know, you had, let's say, these op-amp, these transistors that were all biased in their active region. You may turn one of them off. The current that was used for the biasing of that transistor is going to go and charge up a capacitor. A current source biasing a capacitor gives you a constant voltage going up or down. And that's why this happens. So usually this is happening because you have turned off a transistor that was in your signal path. You didn't want that to happen, but the large signal amplitude did that to you or to your op-amp. And you passed the current that was used for biasing of that transistor through a capacitor that you have inside the chip. You get a constant rate of voltage at the output. You can actually go and estimate how much those capacitor or the current is if you know one of them. And this is it, right? So you basically, after that, because your device is off, it doesn't matter what your input does. You know, if you increase the input signal amplitude or decrease it, that will not change. So this slew rate limitation is another factor that limits how you can use your op-amp. If your signal is changing too fast, even if it is within the bandwidth, if the changes are too fast, you may hit this limitation. So, for example, for this sinusoidal circuit here, sinusoidal signal here, if this is your slew rate, well, it is a constant value, but your sine wave can have a varying slope over time, varying rate of changes over time. And the worst case scenario actually happens at the zero crossing. So if you look at the derivative, so let's say if Vn or V out, ideally, let's say ideal, was some Vp sine omega t, right? So this is your Vp. Now, if you look at the derivative of V out, how fast it changes with time, it's going to be Vp times omega times cosine omega t, right? Now what happens is that zero crossing points at t equals 0 and then 2 pi over f and so on and so forth, you have the maximum slope, right? You have the maximum slope when this cosine omega t is 1. And what is the maximum dV out over dt? So for a sine wave, maximum slope or fastest change or maximum rate of change is Vp, the amplitude of your signal, times omega. Right? So Vp cosine omega t, but cosine omega t, the maximum value is 1. So this is the fastest change at the input for a sinusoidal input, the fastest rate of change of that signal for a sinusoidal input. And if your slew rate is larger than that, if your op-amp can handle a change in the output voltage that is larger than that, great, you don't see any problem. However, if the slew rate of the op-amp is less than that value, then for a sinusoidal input, you will have issues. So for example, you may have a signal that is not that big, but the frequency is very high. Or the amplitude is high, even though the frequency is small. You know, it's Vp omega combination. You may have the slew rate limit. So let's go back to the example that we had. So example we had was the op-amp with an open loop gain of 10 to the 6 and omega b of 10 radians per second. But let's assume that we have a number for slew rate. So assume the slew rate limitation for that op-amp is, let me use the numbers I have here, 1 volt per microsecond. So this is as fast as the output voltage can change. Nothing can be faster than that. So the question here is that, and let's say gain of 100 as we had before, for an inverting op-amp. All right, so this is the same example. I just divided it into 2 sections for bandwidth and slew rate limitations. Now, the second part of the question says that what is the maximum signal amplitude if we want to have a distortion-free amplification, right? And so let's say for a distortion-free, meaning that we don't hit the nonlinear limits, for a distortion-free amplification over the entire bandwidth of the device, what is the maximum? So this is a bit of bad writing, so maybe I should have started with what is the maximum input signal okay. So from the discussion in the above, I remember that AV0 was 10 to the 6, omega B was 10 radians per second, and from there we find out that the bandwidth for this device is 10 to the 7 divided by 100, the gain of the stage, so 10 to the 5 radians per second. This is what we solved in the previous section. Now, if I want to have the full bandwidth, what is the largest signal I can amplify? So the slew rate limitation is going to put a limit on the amplitude of the signal. You know, from the first part, I don't have any limitations on the amplitude. It's just the gain and the bandwidth. Now I have a limitation on the amplitude of the signal. So what I can see is that at the output, the slew rate is maximum change at the output, right? And we saw that for a sinusoidal input, this is Vp, the peak of the signal, times omega of that signal. Because we want to have that distortion-free amplification over the entire bandwidth, I already know this omega, so I'm going to say the fastest signal I can have, so it's omega, the new bandwidth that I have here. So therefore, I can see that Vp times the bandwidth that I had, 10 to the 5 radians per second, this has to be less than my slew rate limitation, at the limit maybe equal to slew rate limitation. So 1 volt per microsecond, so that's going to be 10 to the 6 volt per second. The units are the same, so this is radians per second, remember? And that's Vp. So the units are the same on both sides of the equation. And this tells me that maximum Vp at the output is 10 volts. So 10 to the 6 over 10 to the 5, or 10 volts. Okay? I have a gain of 100, so therefore maximum input signal amplitude is going to be 10 divided by 100, or 0.1 volt, which is very respectable, right? So this is a good op-amp. It's doing a good job for, even for these high frequency signals, relatively high frequency signals. It's giving you a good bandwidth and fast response. And that's it for the course. We have covered all the material that we needed for this course. I'm going to have the live sessions all the way to the end of the semester, and then what I'm going to do in the first live session is probably going to discuss some of these op-amp circuits, and then the final one I'm going to assign it to reviewing the course material and providing you with a brief history of electronics, all the way from the vacuum tubes to now with the most advanced CMOS technologies and what happened in between. So it's going to be a fun lecture if you're interested in the history of technology. Formally, we are done with the course material. I will have the live sessions, office hours, and I'm happy to answer questions that you may have. And thank you for attending this lecture and basically sitting through these challenges that we are facing due to the COVID pandemic. Hopefully, we'll provide you with a chance to gain some hands-on experience with electronics. If you know the material here and if you go and play with the simulator that you have on your computers, you will gain the insight necessary to design these circuits. And then with the hands-on experience that you will hopefully gain at some point in the near future, you can take care of, I would say, with the material that you learned in this course, 80% to 90% of the circuit design applications, analog circuit design applications or problems that you will face in future. There are some issues we didn't discuss, most important of which is noise, but there's also bandwidth issues, maybe filtering issues, and those are covered in other courses. But as a mechatronics engineer, the foundation that you have gained in this course hopefully will be serving you in, I would say again, 70 to 80% of the situations in future. So thank you again for your patience through the whole semester, and best of luck to you with this course and other courses and your careers. Thank you.